Okay, let's talk about robust regression. So we've talked about what it means to have outliers, but we haven't really talked about what to do when you observe them. So when we have outliers, we know that least squares doesn't perform well. And just as a recap, how can we tell if we have outliers? If you don't remember, go back and watch that video on unusual observations, and there's a couple different ways in there to detect outliers. There are methods out there to specifically deal with cases where there are outliers, and specifically when you don't want to be removing those outliers. And so quite often when we see kind of unusual observations that look different from what we would have expected in the data, often those are real. They don't necessarily need to be deleted. Of course, if it's a data entry error or something like that, then that's a different story. But a lot of times outliers are real observations, and so using methods that take them into account, but that will still give you kind of a robust result, if you will, can be helpful. And so that's what we're going to talk about today. And so there's this concept known as M estimation, and you've already been doing it because least squares uses this methodology, but it's just basically more general. And so essentially it modifies least squares to pick a beta that minimizes this general objective function. So you have some function of your residuals here, yi minus xi transpose beta. And so what would that function be for least squares? What's the function that's in here? What are we minimizing for least squares? With least squares, we know that we're minimizing the residual sum of squares, and so that's going to be equivalent to f of e squared. So if this is our residual in here, so it'd be it's just going to be the f of e is just going to be e squared here. So that would be y minus x transpose beta squared. That's the thing that we're minimizing. So there's lots of different possibilities for this function. In general, you can think of there's certain characteristics that you'd want these functions to have. Maybe you want them to be monotonic, and there's various rules for setting these M estimators. But we're going to talk about three forms of this today. And so the first is just going to be the normal least squares, where the function is just equal to e squared. So just the residual squared. And the second, this is known as least absolute deviation regression. And so that would be if you set this equal to the absolute value of e. Sometimes we call this the L1 regression as well, or L1 norm. And then this third one is it kind of splits the difference. This is known as Huber's method. And basically it falls somewhere in between if you were to do least squares regression and this least absolute deviation regression. And so in this case, you would have it be e squared over 2 if e is less than or equal to c, or it'd be c times the absolute value of e minus c squared over 2 otherwise. And so this possibility is going to be the one that we're going to be focusing on today here, where it basically falls in between these other two methods. So then you're going to differentiate the subjective function with respect to beta, and you're going to set it equal to 0, which is going to produce a bunch of estimating equations. So it's going to look something like this. And it turns out that you can actually define a weight function such that this weight function is equal to that derivative. And so solving that is actually going to be the same as solving weighted least squares, which is great because in the last class you learned how to do that. And so you would just be minimizing the sum of wi squared ei squared, so this weight here. But it needs to be solved iteratively. And that's because these weights that we're about to discuss in this kind of M estimation space, the weights depend on the residuals, which the residuals, of course, we know we get those from the estimates. So the residuals depend on the estimates. But the estimates depend on the weights. So we have kind of this circular problem. And so the only way to be able to solve this is iteratively. And so previously, when we were talking about kind of different, like for the generalized least squares, for example, we had a fixed sigma that we were starting with. And now basically we can start with something, but we're going to iteratively work our way towards the correct weights here. And so that's what this iteratively reweighted least squares is, or IRLS. So this is the process. You start by selecting values for beta. So we call these just beta 0 or beta naught maybe. It's basically the starting values for those betas. A sensible one might be the least squares estimate for beta. And then at each iteration, you calculate the residuals for the previous iteration and the weights from the previous iteration. So if you're on iteration t, you calculate the residuals from iteration t minus 1 and the weights from iteration t minus 1. And then you solve for the new weighted least squares estimate. And so our new beta t, so the beta in the tth iteration, is going to be equal to x transpose, and then using the weights from the previous one, so w t minus 1. And so that w, if you recall from weighted least squares, is just going to be a diagonal matrix with those weights wi on the diagonal and zeros everywhere else. And then times x. Then take the inverse of that, and then x transpose w t minus 1. So this is, again, the weights from the previous iteration times y. And then you repeat that over and over until it converges. And by converges, I mean basically you keep doing it until the weights from one iteration to the next have really small differences between them. And so from our methods that we talked about, the least squares or this kind of hybrid Huber method, or this one where we take the absolute value, they each have an objective function when we're talking about it in terms of M estimation. So least squares, it's the residual squared. For the next one, it's going to be the absolute value of the residuals. And for this final one, it's going to be this equation where it's going to be e squared over 2 if the absolute value of e is less than or equal to c, or c times the absolute value of e minus c squared over 2. So these are the objective functions. These are the things that we're minimizing. And each of these have a corresponding weight function. And so obviously for least squares, we're not doing any weighting. So the weight for all of the values, the weight for all the observations is just 1. So there's no, that, if you plug in a matrix that has zeros on the diagonals or on the off diagonals and 1 along the diagonal, it's just going to be the identity matrix and it'll give you the exact same answer. So if you plugged in this, you would just get least squares. In the next example, the weight function is going to be 1 over the absolute value of the residual. So if you plugged in that, you would get this. This would be the thing you're minimizing. And in our final example, the one that we're going to be using for robust regression, the weight that you can plug in is going to be 1 if the absolute value of the residual is less than or equal to c, or it's going to be c over the absolute value of the residual otherwise. And so this method combines the down weighting of extreme cases with equal weighting for middle cases. So it basically takes this nice approach where we end up having equal weighting, so we just have a weight of 1 for normal cases, but then for our extreme cases, we end up down weighting them like this, and we downweight them by c over the absolute value of e. So you can do this in R using the RLM function from the mass package. So it looks just like this. It's going to be the exact same form as when you use GLM, but it's RLM for robust regression. And then you can examine the weights like this, and so you can pull the weights out of, if you call this mod, so if you fit the model and you call it something, you can pull out the weights object from that model object like this, and that will give you the weight for each of the observations. And so what that's going to mean is basically they're going to be 1 for observations that sort of look like they're kind of in the normal range. And for extreme observations, ones that seem like they might be outliers, they're going to be downweighted, so they'll be less than 1. And so you can look at those weights to get an idea for sort of which observations were potentially a little more extreme. So this is useful, again, for when there are outliers. So if you find the result from least squares regression and robust regression noticeably different, so if you fit your least squares regression model and then you try a robust regression model, and you find that they're giving really different results, that probably means that robust regression is more trustworthy and that least squares is maybe not fitting quite right, most likely due to outliers. Now, of note, robust regression does not help with leverage points, and so if you don't recall the difference between those, make sure you go back and review the unusual observations lecture, but this is not something for leverage points, it's specifically for outliers to help with that. Okay, so your application exercise. I want you to fit a robust regression model to the gala data from the faraway package, and I want you to predict species using area, elevation, nearest, Scrutz, and adjacent. And once you fit that model, I want you to check which observations result in weights less than 1. And then I want you to describe what that means about these observations. So what can we tell about these observations based on the fact that they end up with weights less than 1 in this model? So go ahead and work on that and upload it when you're finished.